Yes, because of time, I will not do a big introduction, but here we are pleased to present Greta Lanzarotto and Ludovico Pernata from both from the University of Pavia, and they're going to talk about extended Busa canons.
Good morning, everyone. Can you hear?
Yes. Yes.
Okay. So I am Greta Lanzarotto, a PhD student in mathematics from University of Pavia in Italy. And today, me and Professor Ludovico Pernata, also from University of Pavia, are going to present some results on tiling rhythmic canons, in particular on what we have called extended Busa canons. But first of all, I would like to thank the organizers for allowing us to present online and express our regret to not be there physically and thus experience the MCM conference fully. So I leave the floor to Professor Ludovico Pernata, who will introduce the topic Busa canons and extended Busa canons.
Thank you, Greta. I also want to cheer you all. I hope you are enjoying the conference, and we are very sorry to be far from you. The topic of the talk is extended Busa canons, but of course we will start giving some definitions, and then I will leave Greta to talk to you about the results we got. Well, this is the brief summary, some definitions about canons and models of canons to treat them mathematically. And in the end, as you see, we will end up talking about the extended Busa canons. Well, the first definition is probably known to all of you, but we give it for completeness. So a rhythmic canon is a composition which is essentially made of a single motif translated in time. It can be sometimes allowed to be modified with some transformation to maybe reverse the order or multiply the intervals, but it is essentially the same motif which is used several times. So we can call this canon C as the union of the translations or transformations this motif goes under in our piece of music. We will talk only of rhythmic canons, so we will disregard tonality or even any other musical effect apart from rhythm. So the canons we will talk about are tiling rhythmic canons. This special kind of canons is characterized by the fact that there is no modification, so there's only translation in time, and but the voices must be complementary. That is, at every time there must be one voice speaking, but just one voice. There will never be two voices singing at the same time. This, of course, gives rise to a combinatorial problem. Some of you know very well, and we will give a small example for those who maybe don't know the subject. This is a very small canon. You can see we can represent, as many times it's done, time on a circle in this case, because the canon will repeat itself after a certain period of time. And this period of time is called n in this slide. So the n is equal to 9 in the example. But along the circle, so at different times, different voices will sing, and we have colors that identify the moments where voices sing, and you see that the pattern is the same, only shifted in time a certain amount. This is sometimes called Kreinek diagram from the 30s, maybe. And well, later, I don't know if this is simpler or more difficult to understand, but there is another model you can do with squares. This on the right, it is the same canon. It is only written in a different way. Every voice has a line, has a row, and well, black squares are the times where the voice is singing. You can see that at every column, so at every moment of time, there is only one and only one voice active at that time. We sometimes called one of the voices inner voice and the other one outer voice, because, of course, from a musical point of view, one is the motive, and it will be the inner voice. The outer voice represents the moments, the starting points of the voices. So it's not a completely symmetrical object from a musical point of view. But from a mathematical point of view, the two are indeed the same. They're completely symmetrical. And in fact, of course, you can also make the other way, the other canon in which B is the inner voice and A is the outer voice, and you will obtain another canon with the same period, N9 in this case. When you want to analyze canons from a mathematical point of view, one of the most useful models is the polynomial one, because there is we are talking about a very special polynomial. The polynomial has one monomial for each instant of time, and of course with increasing exponent from 0 to n minus 1. And the end result is that at every time there is exactly one voice singing. So the end result must be the polynomial which has every monomial with coefficient 1. So 1 plus x squared plus x to the power 3 and so on up to x to the power n minus 1. But if you check what happens for the two voices, it is very easy to see that the canon is represented by the product of polynomials. This is a very important feature, because it means that polynomials are very well suited to analyze rhythmic canons. Of course, this would not be the case if the canon were also not only rhythmic, but it also carried a melody. We are speaking of a very simplified structure, and this simplified structure can be modeled by polynomials. But this polynomial is a very famous one. So we know that it can be written as x to the power n minus 1 divided by x minus 1. And we know that this is the product of all cyclotomic polynomials with order a divisor of n, well, bar 1, since we divided by x minus 1. And this means that the product, say, mod x to the n minus 1 is exactly the product of all the cyclotomic polynomials. This means that A and B must be a product of a part of the cyclotomic polynomial that divide n, and the union of the divisors must be of of the cyclotomic polynomials which divide A and the polynomials, the cyclotomic polynomials which divide B must be the whole set of divisors of N. On the other hand, this is an equivalent condition, so we can completely transform the problem to an algebraic one if we want. This could be a very good news, but in fact, the problem is still not easy. And the treatment with polynomials is promising, but it's not completely, it's not solving every question we can formulate. What is important about these polynomials is, of course, that they can only have coefficients 0 or 1. Well, 0 is normally not considered a coefficient, but anyway, the only possible coefficient is 1. This type of polynomials is called Newman polynomials and has been extensively studied in complex algebra, but not many of those results apply to our situation. Many things are known, but apparently not much is useful for our problem. Of course, there can be some, say, easy canons that you can make. This is when one of the two voices is periodic. And if one of the two voices is periodic, what happens is that you simply have to fill every beat of the small period of one of the voices with beats of the other one, maybe at distant times, and you will get a canon. This is very easy, but of course, one realizes that soon that they are not the only possible canons, and as you can imagine, the most interesting ones immediately become the other ones, the aperiodic canons. It is a theorem of Hayes that, in fact, for some n, there cannot be aperiodic canons. This is a set of integer numbers, which gives rise to the notion of Hayes group. And as you can see, an Hayes group cannot be decomposed as a sum of two subsets if both of them are aperiodic. One of them must be periodic, and this means that the canon which we could build with the two sets will have one periodic voice. So we will start with the quest to find aperiodic canons, and as you see, well, there is maybe to call period the number n is a bit unfortunate because it seems a bit contradictory to speak about the period of an aperiodic canon. Beats. And a different thing is the fact that inside this number n, the canon can have its own periodicity, a smaller one, a divisor of n. If this canon has no smaller period, it is called aperiodic. Well, as we said, the numbers for which there are Hayes groups have been classified, and you can see them in this slide. A theorem can be attributed to Wooza because he gave the construction to build aperiodic canons for the bad cases. They were called bad groups, but in fact for us they are good groups because we are studying aperiodic canons that happen only when n is bad. This is the classification. The second set is the set of, say, Ayers numbers which such that Z mod, the numbers mod n are an Ayers group, so there's no aperiodic canon in that case. While the first set, nu, is the set of numbers such that aperiodic canons exist. And of course, you can probably realize that nu is far bigger than H, because H is made only of powers of a prime or of at most 2 primes, or maybe 3 or 4 primes, but only with very small exponent. So the vast majority of integer numbers is in fact in the set nu. So we have a lot to search for aperiodic canons. The first, as well, I anticipated, there is a construction to build aperiodic tiling rhythmic canons for n's in the set nu in the previous slide. And this is a theorem that can be attributed to the 3 of these authors, Ayers, De Bruyn, and Wooza. They proved it in parts. Wooza studied it in a long paper in 4 parts that analyzed the situation in a deep way and gave one possible construction, proving finally that these numbers are in fact, say, bad. But it is natural to ask oneself if there are other constructions, or this is the only way to construct aperiodic Italian rhythmic canons. And well, after some years of research, other constructions appeared. One that we want to present is the Jędrzejewski construction. Again, of course, we are speaking about number n of this type, but we fix P1 and P2 prime numbers, and we impose that the greatest common divisor of P1 and 1 and P2 and 2 is 1. Well, in this case, it is possible to generate an aperiodic rhythmic canon with this construction. You see, well, we will see maybe a clearer picture in the next slide, but what I described here is only that the 2 parts of the canon have a very different role. The first one, A, is just, say, a direct sum of 2 pieces, while the second part, B, is the union of 2 subsets. So if you make direct sum, it is more or less as taking the product of the polynomials. So the cyclotomic polynomials that divide A are just the union of the cyclotomic polynomials that divide A1 and those which divide A2. While the cyclotomic polynomials dividing B are not the union of the 2, but the intersection of the cyclotomic polynomials dividing the first part and the second part, plus maybe some other cyclotomic polynomials that may appear when you take the union. In this theorem, you see that we have that B is not periodic as an hypothesis. There is no indication of when this happens or not. Well, to give an example, we took n equal to 216, which is not a very small number, but it is one of the first possible numbers where something interesting happens. And because you can imagine that you have to be a product of at least 5 different prime numbers. So 72 is the smallest possible number. But of course, to have interesting examples, maybe you have to go higher. And well, this construction gives you one of the possible aperiodic canons that can be defined in this way, but of course it doesn't say that much if you only see the numbers. So we try to produce a graphic scheme, and in this picture on the left, you see the orange factor, which is a piece of B, and the purple factor, which is A, and they represent all the divisor, the cyclotomic polynomials with order a divisor of 216 that are a divisor of A or respectively of B. As you can see, A is a product of 2 factors, and these are in fact these 2 lines, these 2 purple lines. One goes from 4 to 108, the other one goes from 9 to 72. And these 2 lines are in both pictures, while B has 2 parts, as we saw, and the 2 parts are in 2 different colors. And we will have to take the intersection of the cyclotomic polynomials, dividing them. So we will have a part of the complement of the purple set. There are a few cyclotomic polynomials left, so 2, 3, and 6. But if you examine the example carefully, you'll see that the 6 classes 0, 4, 1, 2, 3, and 5 with this apex, which means that they are taken in the subgroup generated by 6 in 216. They will say they have 1 element for each class, remainder class modulo 6. So if you take all of them, they will compose the polynomial x to the power 6 minus 1 divided by x minus 1, which is the product of exactly the cyclotomic polynomials of order 2, 3, and 6. Well, this example is already constructible with the Niederszewski construction, but we wanted to do a little more, so we imposed some more conditions. And the conditions are in this slide. You can see that we fix again by P1 and 1, P2 and 2, and N3, such that the greatest common divisor of P1 and 1, P2 and 2 is 1, but we don't ask for P1 and P2 to be prime. We only ask, but this is only a technical hypothesis that we could also leave out. It is only to give tedious results. We could have uglier results taking this hypothesis away. That there is no prime Q dividing N3, but not the product of the other ones. And then we will, well, define a few sets that are usually used to define the canons in the next slides. But I will skip this. Of course, they are only tools to define. And we can give the first theorem of this talk and of the thesis of PhD thesis of Greta, which is, say, a slightly stronger form of the previous construction. As you see, we still have A1, A2, and the 2 parts of B, as before, but we are not asking the P1 and P2 to be prime, and we can prove that the set B is a periodic under this hypothesis. So, well, the existing construction has been a bit generalized, but well, for further generalization, I leave the floor to Greta, which will take you to higher results in the topic.
Thank you, Enrico. Maybe next slide. First, a generalization of theorem 1. See V as the disjoint union of 3 different sets. And you can see U1 plus V2 plus K1, U2 plus V1 plus K2, and W plus K3. As in previous theorem, we have the first 2 parts of B, which are respectively periodic modulo n over P1, and the second part is periodic modulo n over P2. And we introduced a new set W, which is which is periodic both modulo n over P1 and n over P2. So this is the main point of this theorem. Okay. To proof, we see first of all that we ensure that B is a periodic because we have a periodicity of the same period only in 2 of the summands in B. So there is no way periodicity of the same period in all the 3 pieces. And to prove that the sum of A and B is equal to Zn, we use some equalities proved by Jedrzejewski, and so that A1 plus U1 plus V2, as defined in our general hypothesis, is equal to A1 plus U1 plus V2. And at the end, we see that the sum A plus B is the same as H plus K, which by hypothesis we set equal to Zn. Also, we have a cardinality argument which ensures that the sum A plus B is direct. So we have essentially a Thalion rhythmic canon of order n. Okay. So here we have the example with the canon of period 216 and the parameters 2, 2, 3, 3, 6. So you can see that we have making a comparison with the previous example. We have split our previous K2 set into 2 parts. So now we have K2 equal to 21 and 43, and K3 equal to 122 and 167. And we have introduced this W part, which is in this case 36I6. So in the next slide, we see the graphic representations providing the lattices of divisors of n. So the indexes of all the cyclotomic polynomials which divide A of x or B of x. So in the first picture, we see the representation of the U1 plus V2 part. So you can see that this part is periodic modulo 72. And graphically, you can see this because we have a sort of what we can call a maximal hyperplane. So the extreme segment of the lattice, which is which connected 27 to 216. And then we have the second picture, which represents the periodicity of the second part, U2 plus V1, with period 108. And the third part is represented by W, which is periodic both modulo n over P1, so modulo 72, and also periodic modulo with period modulo with period n over P2, which is 108. And then in the last row, you can see that we have chosen the K1, K2, K3 sets, which are whose disjoint union gives a complete set of cosets representatives for Zn modulo H. So we have 0, 1, 2, 3, 4, and 5. Okay, so another generalization of theorem 1 widens the definitions of sets A1, H2, V1, and V2. And we have substituted sets A1 with sorry, can you go to the previous? We have A1 tilde A1, which is a complete.
About 2 or 3 more minutes. Is that okay?
Yes. Okay, so we have generalized the definitions of A1, H2, V1, and V2, providing more general representatives in the various Cypriot groups you can see in the slide. Okay, so maybe I can go to the. This is the second generalization of theorem 1. And next theorem is okay. So we can call all these constructions, all these canons constructed with these theorems, Busa canons. But we can also consider more general constructions. And by next theorem, we consider instead of K being a complete set of cosets representatives of Zn modulo H, we consider 2 factors of Zn3, which are L and K, and we split these 2 factors, one with A and the other one split into 2 sets, K1 and K2. And so we have a new factor in A. We can see this theorem in the following example. So we choose, in this case, we have M3 equal to 6. So we chose L and K as factors of Z6. And then we assigned L to A and K split into K1 and K2 to B. So in the picture, okay, you can see we have added the factor I2 in both the pictures. We have represented in purple the single cyclotomic polynomial phi2. Also, and with the original parts A1 and A2. And finally, the last construction is provides a sort of extension of factor L, because we proved that if A plus B is a Busa canon, and is a Italian rhythmic canon, and B satisfy condition T2 by Cohen and Meyerowitz, then also the extension of A, which is defined starting from the prime powers of the cyclotomic divisors of A of X, is a new type of Italian rhythmic canon. So in the following example, next slide. Sorry. Okay, so we can call this type of canons, which provide the new factor L, extended Busa canons. And we can also consider the combination of all these theorems and call them again extended Busa canon. The last example in the picture, the following slide, you can see that the factor P2, so the set I2, which is originally L, is extended to embrace also cyclotomic factors 10, 30, and 6. And so we have constructed a new type of Busa canon. To conclude, we provided some tables showing how many Busa and extended Busa canons we can construct with the different theorems. And in particular, in every column, you can see how many aperiodic rhythms, tiling rhythms, you can construct with the corresponding theorem, and not with the previous ones. And in the case you see some green numbers, this means that this type of aperiodic tiling rhythms can also be produced by different choices of parameters. As you can see in the second line of orange section, there are gray numbers which represent the same tiling aperiodic rhythms in the first row. So thank you for your attention. We would like to continue our study, especially maybe trying to erase the third condition we assumed, and maybe trying to reach a general construction for aperiodic tiling rhythmic canons.
Yeah, I was wondering if you had considered the application of this work, thinking generally about channels of information to maybe information theory and cryptography and such like that. I can imagine a lot of uses for this sort of kind of quote unquote random aperiodic blocks of information in different channels summing up to a full channel, something like that. I was wondering if you had considered other applications to fields like what I just mentioned, information theory, other than music theory.
Well, as far as I can say, this has not been considered yet, but it is true that there is also a different possibility to study aperiodic rhythmic canons with discrete Fourier transform, and you can imagine that this is directly linked to information theory. So I suppose that the link is there, but in fact I don't think it has been considered yet.
Okay. Well, thank you so much, and we wish you were here, of course.
We
Thank
will
you.
meet again soon.
Yes.
Thank you very much.
Thank you.
Dunque, ora forse dovremmo poter parlare senza che ci senta nessuno.
Non credo. Bene. Io credo ti...
Dicevo, mi dispiace perché devo aver parlato tantissimo. Non so quanto tempo ti ho lasciato, ma pensavo di essere andato abbastanza veloce, ma invece non tanto.
No, spero di non essere andata troppo veloce io.
No, beh, alla fine hai dovuto saltare un paio di slide, però non sono sicuro che il pubblico avrebbe seguito ogni dettaglio della seconda dimostrazione. E comunque mi sembra hai parlato bene, cioè spero tu sia soddisfatta, mi sembra che sia stata piuttosto
Dai,
chiara.
sì.
Vabbè.
Adesso scappo a fare la visita per la patente, se no al 29 sono senza patente.
No, certo.
Va bene.
D'accordo, senti, ci risentiamo presto. Questa è fatta, quell'altra è fatta, insomma, cioè il CPIOR, quindi siamo,
D'accordo.
tutto va bene. A presto.
Va bene, grazie. Ciao.
Ciao ciao.